Well, that was fun. Get your notes ready, get your pencil ready, and get your periodic table out because we're going to be studying something called shell models and Lewis structures, also known as electron dot structures. All right, students, so what we're doing is we're going to be learning about the shell model of the atom. And we're also going to be learning about a new and improved model called the Lewis structure. Wonder who that was named after. Sometimes scientists are a little bit conceited, if you ask me. This is also known as the electron dot structure. All right, here's a little warm-up, which you should be able to do. So if you'd like to pause the video and answer the questions before I give the answers, then go ahead. Number one says to draw a general picture of the atom, label where the protons, neutrons, and electrons are. So I'm going to draw some 2 protons, some 2 neutrons, and I'm going to draw 2 electrons outside in the electron cloud. Okay, and this is actually the helium atom. Okay, that's the one I drew. These are where the electrons are, protons and neutrons. There they are. What is the electron charge for a proton? We should know that's positive. Neutron is no charge, and electron is negative. That's a positive for proton, no charge for neutron, and a negative for electron. How many protons do carbon, calcium, and uranium have? That's 6, 20, and I want to say 92. There it was, 92. Okay, that's your review. Okay, let's get going in here. So here's an atomic structure. Has the protons and neutrons are in the nucleus. Everybody see that tiny little dot right there? Well, this is more of like the correct scale of how an atom actually is. This tiny little dot is the nucleus that contains all of those protons. Like for example, uranium with its 92 protons, it would be located in such a tiny little space. Well, what is this whole thing? It's mostly the electron cloud. So atoms are mostly empty space where electrons fly around the electron cloud. So there'd be lots of electrons flying around everywhere in here. There's an analogy that says that if a football field was scaled to be like the size of an atom, then if you put like an ant, like a football stadium, not field, excuse me, like a football stadium, like an NFL football stadium was the size of an atom, and you put an ant right in the middle on the 50-yard line, that ant would represent how small the nucleus is compared to the rest of the atom. It's small, but it carries most of the weight of the atom. It has most of the mass of the atom in the nucleus. Yep. All right. Electrons are constantly flying around in the electron cloud, but there are locations where they are most likely to be. Okay. Nobody actually knows where an electron is located at any given point. We just know where they've been by a little shadow. Take a picture of it and it shows where the shadow is. There's a shadow there. And you keep taking a million pictures and you get an idea of where all these little dots appear, and you get all these different electron areas and shadows. Okay, so we're learning about the shell model. So we're going to talk about electron shells. All it is a visual representation. It's not real. Visual representation of where the electrons are most likely to be. So if here's the nucleus, we have shell number 1 with 2 electrons, shell number 2 that can have up to 8 electrons, shell number 3 that also can have up to 8 electrons. These are shells, remember. Electron shells are not real. Electrons do not orbit around the atom like planets revolve around the sun. What's really happening is looking something like this. Okay? Like that, where electrons are in there somewhere. Okay, so why is it important to know like where the electrons are? Why is it so important to think about how many electrons are in the first shell, second shell, or third shell? There's a reason for it, and we'll take a little break to draw right here. So if here is atom number one, we'll call it hydrogen, and it has the one electron. And then here's another atom over here, chlorine, and chlorine actually has. Let me just do this for you. Oh well, yeah, we'll change. We're going to change it to fluorine just because it's easier. Because I don't want to draw that many electrons. It's too many electrons to draw. So fluorine has the 2 electrons in the first shell, and it has 1, 2, 3, 4, 5, 6, 7 electrons in the second shell. Just kind of draw that, and you can imagine there's lines in between right there. Let's complete that real quick. I just didn't want us to get confused between the negative signs and like the circle. Okay. So when this atom gets in contact with this atom, they're attracted. Okay. What's the first thing that touches? The first thing that touches is the electron cloud, not the nucleus. It's almost like the nucleus is safe in the middle, and the electron cloud is touching you. The electron clouds are touching. Okay, and this is actually the theory for chemical reactions, is that when atoms interact with each other, it's their electron clouds that are interacting with each other, and different things can happen, causing different chemical compounds to form. So in this situation, what will end up happening is fluorine, with its 9 protons in the nucleus, it's like a giant magnet in there, giant positive magnet. There's 9 of them. We put a little nine positives, and hydrogen only has that 1 positive in there. That's very bad. I should write. There's 1 positive proton in there. I should write the symbol for proton. 9 protons, and 1 proton for hydrogen. Okay, so what ends up happening is fluorine's 9 magnets, like 9 positive charges, ends up snatching away this electron, and that electron moves over there, and you end up getting hydrogen with just a positive charge because it's only a proton now. There's no more shells. There's no more shells on hydrogen. Then you end up getting fluorine with a -1 charge because it gained the electron from hydrogen. And then they come together to form the compound hydrogen fluoride, or hydrofluoric acid. Okay. Okay, so more about shell models. Okay, so these are the instructions on how to draw a shell model of an atom. You can write them down because we're going to be following them. So the number of shells an atom has equals, which is the same as the number of the row number on the periodic table the element is on. So we just did, for example, we did hydrogen. And if you notice, hydrogen's just on the first row. There's only 2 elements on the first row. So hydrogen only has 1 shell. And that's why we drew hydrogen like that, with just 1 shell. And then fluorine right here, notice that it's not on the first row or the third row, it's on the second row. So these are the rows going from left to right. These are the rows, and these are columns going up and down. Columns go up and down, rows go left to right. So fluorine is on the second row. Second row. That's why we drew fluorine with 2 shells, just like that. Okay, so going back to the notes, oops, dropping the pencil. Going back to the notes, it says that the max number of electrons in each shell equals the number of boxes in each row. Okay, so for example, with fluorine that we drew earlier, Remember we drew the first shell with only 2 electrons? Well, there's a reason for that. If you look at the periodic table, the first row only has 2 boxes, 1 box, 2 box, the hydrogen and then the helium. So that's why there's 2 electrons on the first shell. Shell, yeah. And that's why there's 1, 2, 3, 4, 5, 6, 7 electrons on the second shell. 2 electrons on the first shell, 7 electrons on the second shell. Let's count them. 1, 2, 3, 4, 5, 6, 7. That's a total of 9 electrons. That makes sense because 9 electrons plus the 9 protons in the middle gives us an atom that has no charge. There's an equal number of protons and electrons until they actually interacted with each other. And then the fluorine took away hydrogen's 1 electron. And then they became ions. See down there, they became ions. Okay, so this all relates to ions too. Okay, so now we're going to practice drawing the shell models for lithium, nitrogen, and radium. Go ahead and push pause and try and do it on your own. Okay, here we go. So for lithium, we need to, step number 1, determine the number of shells an element has. And we know that that's the row number on the periodic table the element is on. So if we find lithium on the periodic table, there it is right there. You can see that it's on row 2. It's on the second row. Okay, so we know that lithium has 2 shells. So let's draw it. Lithium, 1 shell, 2 shells. Dang it, I thought that was going to fit better. There we go. Okay. Then the second step is that the maximum number of electrons that you draw on each shell, it equals the number of boxes in each row on the periodic table. So the first row on the periodic table only has 2 electrons that could fit inside of that shell. And we know lithium has a total of 3. So we have to draw the first 2. We just draw dots. We don't have to write the E minus like I did earlier. And then we go to the second row and lithium has the first box. So that means there's 1 electron drawn, and that's lithium. Let's do nitrogen. That's the shell model. That was the shell model for lithium. I did not want to stay up there like that. Stay up there. Okay. Nitrogen. We find nitrogen on the periodic table, and we're following the rules right here. The number of shells on an element has equals the number of rows on the periodic table the element is on. So nitrogen is, where's nitrogen? There it is, number 7. We notice that it's on the second row. It's still on the second row, just like lithium was. So how many shells does it have? Well, it has 2. So here's N for nitrogen, and there's 1, 2. That was a weird circle. Okay, and then the next rule says the max number of electrons in each shell is the number of boxes in each row. So the first row still has 2 electrons in it. So we draw 2 dots in the first shell. It'll always be 2 dots in the first shell. Then next, nitrogen has, counting from left to right in the second row, 1, 2, 3, 4, 5 electrons in the second row. 1, 2, 3, 4, 5. Okay, then it looks like that. And that's it. All right, now we're going to get to radium. Radium. Where's radium on the periodic table? Oh my gosh, this one's difficult to find. Where's radium? There it is, way down here. Wow. Oh my goodness. So step number 1, the number of shells an element has equals the number of rows, row number on the periodic table the element is on. So radium is way, can't even show it. It's way down here. So how many shells is that? That's 1, 2, 3, 4, 5, 6, 7. Oh man, this is gonna be really obnoxious. So there's a symbol for radium. Here's the first shell, second shell, third shell, fourth shell. Okay, how many is that? I don't even know. Okay, so this is annoying. Anybody else agree? Okay, good. If you like drawing that many circles, you got problems. Hey, fool, nobody likes to draw shell models. All right, that was fun. We've established that drawing shell models is a pain in the butt. See, drawing shell models for bigger atoms is a pain in the butt. So instead we draw bada bing, bada boom, Lewis structures. Lewis structures is the easier way to show electrons. Okay, so what Lewis structures are is drawing an atom and the valence electrons only. Uh-oh, that's a new word, valence electrons. They're different than regular old electrons. So that's why I'm drawing attention to it. Valence electrons are just the electrons in the outermost shell. So valence electrons are the ones involved in the chemical reactions most of the time. Okay, remember when we drew our atoms earlier? Our hydrogen, oops, excuse me, not a plus yet. So hydrogen with its one electron, and then fluorine with its 9 electrons. One, two, three, four, five, six, seven. Yep. That's a total of 9 electrons. Okay, so when it says valence electrons, it's the ones that are on the outermost shell. So for hydrogen, since hydrogen only has one shell, that just means that the valence electron is that one electron on that shell. But so we can say it like this, one valence electron. Okay, for fluorine, fluorine has 2 shells. So that means when we're counting the valence electrons, we're just counting the electrons in the outermost shell. We don't care about the inner shell anymore. So we care about 1, 2, 3, 4, 5, 6, 7. So 7 valence electrons is what fluorine has. Okay, that's different than the total amount of electrons. That's something that you need to make sure you note down, that the total amount of electrons is different than the valence amount of electrons. The valence electrons are the ones that are involved in chemical reactions. Well, why? Because when these atoms run into each other, what's the first thing that touches? Well, now you can say the first thing that touches are the valence electrons. Those are the first thing that touch an atom. Okay, so valence electrons. We need to make sure we note this right here. Oops, excuse me. What was that? We're going to ignore groups 3 through 12 when drawing Lewis dot structures. Okay, what do I mean by groups 3 through 12? That's this whole section right here. This whole section right here. They're called the transitional metals, and I'll show you this periodic table. That whole middle section has new rules and different rules for Lewis dot structures, but all the other elements, you can follow the same rules. Okay, so now let's practice drawing some Lewis dot structures. Radium doesn't seem that intimidating anymore. Remember, radium was in the 7th. The 7th has 7 shells, but how many electrons are in just the 7th shell? How many valence electrons does radium have? Well, just 2, the 87th electron and the 88th electron. So when you draw radium's Lewis dot structure, it'll look like this. Okay, there's a shell, and there's the 2 electrons, just like that. And we'll start on the top and go go clockwise. But actually, Lewis dot structures are even easier than this because you don't even have to draw the shell. So in reality, we're just making it super easy. We're just going to draw the 2 dots. 1, 2, and that's it. That's the entire Lewis dot structure. Okay, so let's try argon, and then you can try bromine. Okay, so argon, if I found it on the periodic table, it's one of those noble gases. It's AR, AR for argon. There it is, way over here. Now, we notice that argon is not on the first row or the second row, but it's on the 3rd row. How many electrons does it have on the 3rd row? Well, it has all of them on the 3rd row. So we count from left to right. 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 of them. So this is how you would draw them in the right order. So argon, we start at the top, go counterclockwise. 1, 2, 3, 4. And then what do? We just double up on the top, right, bottom, and left. So 5, 6, 7, 8. It's like we're doing a little dance. Okay. You go ahead and do bromine, but don't try these because these are different. These are different. These are ions. Ions play by different rules. All right, there's your answer for bromine. It's written right there. What we're going to do is show you the difference between chlorine and chloride. So remember, chlorine, oops, why don't you want to write? So chlorine, I'll write it up higher. Chlorine has 7 valence electrons. How do I know it's 7? Because chlorine's in the third row. We count from left to right, and it's 7. So we draw it like this. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's chlorine. Let's write that. Chlorine Lewis structure. But if I want to write chloride Lewis structure, chloride has a charge of -1. So what does this mean? It has 1 extra electron. So chloride looks like this. Cl, the -1, and then we have 1, 2, 3, 4, 5, 6, 7, and 8. I'm going to go ahead and circle it. This is an extra electron. Why is there an extra electron? Because we have a -1 charge. All right, that's how it works. Can you try oxide and sodium ion on your own? I just realized I made a mistake, so I'm going to go back and fix it. Super important that you understand. Chlorine doesn't have 8 electrons. It's supposed to have 7. That's my fault. I got happy. I was like doing the chlorine dance, 5, 6, 7, 8, and started just drawing all of them. No, my fault. I got too happy about that. But chloride did the happy dance and it had all 8 of them. So chlorine, 7 valence electrons. Chloride has 8 valence electrons. Okay, everybody good? Go back and fix your notes. Okay, so oxide ion. You may have guessed we have oxide with a little -2 or 2-, doesn't matter how you write it. And oxide has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Oxide has 8 valence electrons because oxygen will gain 2 electrons to have the same amount of electrons as the closest noble gas, neon. So that's 8 positive protons, 10 negative electrons for a charge of -2, but it has a total of 8 valence electrons. Okay, the positive ions are actually the more difficult ones this time, because in a positive ion, sometimes the shell is lost. The most outer shell is lost. So then you have a new outer shell. Let me explain it. So here was sodium. Sodium's on the 3rd row and it has 1 valence electron. Okay, because it's in the 1st column, it has 1 box on the 3rd row. Okay, well, when sodium becomes an ion, remember when sodium becomes an ion, sodium loses its 11th electron, so it has the same amount of electrons as neon, 10. Okay, so now that it has 10 electrons, it no longer has an electron on the 3rd shell. Let me give you a visual representation. So here was neon's sodium's 1st shell, 2nd shell, 3rd shell. I'm not going to draw all the electrons, but we know that there's that 1 electron that sodium has. Yeah, actually, I'm going to draw all the electrons. Okay, so there's all of sodium's electrons. Well, when sodium becomes an ion, remember that last electron leaves. There's no longer 11 electrons. It goes away. Okay, so now what we have is a sodium ion that looks like this. It doesn't have 3 shells anymore. It only has 2 shells. And look, that last shell, the outermost shell, now has 8 valence electrons, which means the Lewis dot structure for sodium looks like this. Okay? If there's no electrons in the shell, that means the shell doesn't exist. There's no shell if there's no electrons that are located in the shell. Check out my ID.